You can buy this demonstration from a catalogue. A short, thick-walled cell, windows of solid glass a couple of centimetres deep because it has to hold 37 times atmospheric pressure, sealed, containing sulphur hexafluoride. At room temperature, you see liquid in the bottom, gas above, and a flat line between them. Warm it gently towards 45 degrees Celsius. The line goes soft, wavers, and stops existing. No boiling, no bubbles. It simply is not there anymore. And in the half-minute before it goes, the whole cell turns white. Milky. You cannot see a lamp through 2 centimetres of it. Warm it a little further and it clears. Nothing was added, nothing precipitated, and the fluid was transparent the whole time.
Price the whiteness first, because it is not a small effect that happens to be visible. To scatter light that hard, a clear fluid needs structures about the size of the light. Call it half a micron, about 1,000 molecules across in every direction. Nothing in the chemistry of that molecule has a size like that. Its bonds are a fraction of a nanometer. So the fluid produced a length it does not own, and destroyed it again when you warmed it a degree further.
Produced it out of what?
Out of being at a transition, and that sentence is the whole hour. Charles Cagnard de la Tour watched the boundary vanish in 1822 in sealed tubes of alcohol and ether held over a flame. Thomas Andrews in Belfast did it properly on carbon dioxide in 1869 in a paper called On the Continuity of the Gaseous and Liquid States of Matter, establishing that the liquid-gas distinction ends at a point near 31 degrees Celsius and 73 atmospheres. He saw the whiteness and had no mechanism for it.
When did somebody explain it?
Marianne Smoluchowski, 1908, said it was density fluctuations. The fluid is not uniform. It has patches denser than average and patches thinner. Einstein finished it in 1910 and got the scattering out quantitatively. A denser patch has a slightly higher refractive index, so it bends light. Ordinarily, those patches are far too small to matter. Near the critical point, they are not. The name is critical opalescence.
So the milkiness is telling me a size. The patches have grown until they are as big as the light I am shining at them, which is why they suddenly become visible to it.
That is what it is telling you, and a second thing hidden in it matters more. It is not that the patches grew to half a micron and stopped. Everything smaller is still there. The fluid contains blobs of every size, from the molecular scale up to the size of the light, all at once, which is why the scattering is so ferocious. Whatever wavelength you shine in, there is structure waiting for it.
Take me to the puzzle, because a fluid getting cloudy is a phenomenon and not yet a problem.
Then here is the problem, one of the strangest facts in physics. Put that tube on the bench. Next to it, put a uniaxial magnet, a ferromagnet whose spins are held by the crystal along one axis, up or down, nothing between. Cool it through its ordering temperature. Measure how each approaches its transition, how the order grows, how the response to a small push diverges, how far the correlations reach. You get a set of exponents for each, and they agree. Not roughly, to every digit either experiment can produce.
The two systems have nothing in common. One is argon or carbon dioxide sloshing about with no lattice at all, held together by a weak attraction between neutral molecules that falls off as the sixth power of distance. The other is a crystal of magnetic atoms, with quantum mechanical exchange between fixed neighbours. An interaction that is not even electrostatic in origin in the way the fluids is. Different forces, different constituents, different everything.
Different everything, and finish the list because you will need it later. Different masses, different densities, transition temperatures a couple of hundred Kelvin against 1,000. In one, the thing that orders is a density, with no symmetry to speak of. In the other, a magnetic moment, with a genuine symmetry between up and down. One has a lattice, one does not.
Yet the numbers coincide. Why should anybody accept that?
Nobody should, and the hour exists to explain it. 3 conversations back, we built the mean field construction. The free energy expanded in the order parameter, the trough in the wine bottle, and I left you with its exponents wrong, known to be wrong for 30 years, and the reason? Near the transition, the correlated regions grow without limit until the sample is a froth of ordered patches of every size at once, with no meaningful average for anything to feel.
You left 2 questions on the table, and I have been carrying them since. Why does the froth appear at all? Why should approaching the transition make patches grow rather than merely making the order weaker? And why do systems with nothing in common produce identical, wrong-looking numbers?
Both are mine today, and they turn out to be one question. Answer the first properly, and the second falls out of it, which is not obvious, and is why this took until the 1970s.
Then define the froth for me, quantitatively, because so far it is a word. What do I measure?
A correlation function, built as an operation you could actually perform. Take your uniaxial magnet above its ordering temperature. Pick an atom, note which way its moment points, then walk a distance away and look at another atom. Averaged over the whole sample, the second one points nowhere in particular. The sample is disordered, so the average of anything is 0. But that is not the question. The question is, given that this one is up, is that one more likely to be up than down?
The careful way to ask it is to take the product of the 2 and average that. Then subtract off the product of the separate averages. So I am measuring the extra correlation rather than the trivial part. Is that the right object?
Subtract the averages, always. The object measures departure from the mean and nothing else, and that subtraction is going to earn its keep in about 10 minutes. Now, what shape does it have as you walk away?
It should start near 1, since an atom is perfectly correlated with itself, and it should die. Neighbors know about each other because they interact directly. Further out, the information gets there only through a chain of intermediaries, and I would expect it to wash out.
It dies, and the way it dies is the point. Away from the transition, it dies exponentially, falling by a fixed factor every fixed distance. So the function contains a distance, and no exponential can be written without one. You cannot say, it falls off exponentially, without being asked, per what? That per what is a length, a property of the material at that temperature, and it has a name, the correlation length.
Give me the avatar, because a decay constant is not a picture.
The correlation length is the width of the biggest patch in the froth. Look down on the disordered magnet, not a random speckle of independent atoms, but blotchy, regions that have provisionally agreed, surrounded by regions that agreed differently. The correlation length is the size of a typical blotch. Below that distance, the material has made up its mind locally. Above it, it has not. In the fluid, it is the size of the largest lump momentarily denser than the rest.
How big is it in ordinary conditions?
Tiny. Far from a transition, it is comparable to the spacing between the constituents. A few angstroms in a fluid, a few lattice spacings in a magnet, which is why ordinary matter looks uniform and why a photograph of a fluid at room temperature is boring. Now cool towards the transition and tell me what you expect the correlation length to do.
It has to grow because on the far side the whole sample has agreed. Somewhere between patches a few atoms across and one patch the size of the crystal, the length has to sweep through every scale in between.
Every scale in between, and here is the fact this hour is built on. It does not grow to some large value and stop. It diverges. At the critical temperature, it is infinite, and that is not a way of saying very big. It means the correlation function stops being an exponential altogether because there is no longer a length to put in it.
What replaces the exponential?
A power of distance. and notice why that is the only thing on offer. An exponential has a length built into it, and a power does not. Double your distance, and a power law changes by a fixed factor, regardless of where you started. An exponential cares where you started. So a power is what a function looks like when there is nothing to compare distances to. At the critical point, the correlation falls off as a power of separation, and it never quite stops.
Then guess the divergence with me before you tell me, because I think I can see the shape. As I cool towards the transition, the only thing that changes is how far I am from it. So the correlation length can only be a function of that distance. And if it blows up with no other length in the problem telling it when to stop, then by the argument you just gave, it has to blow up as a power of that distance.
That is the whole reasoning, and you did it without a calculation. Measure the distance from the transition as a fraction of the transition temperature itself, a dimensionless number, 1 part in 1,000, 1 part in 1,000,000, and the correlation length goes as that fraction raised to a negative power. Everybody writes that exponent as nu, and it is the most important number in this subject. Landau's mean field construction gives it as 1/2. In a real three-dimensional system, it is about 63 hundredths.
63 hundredths against a half. That is a small difference for something you are calling the most important number.
Small in the digit, enormous in what it costs to produce. And do the arithmetic on your tube before you decide it is academic. The correlation length in that fluid starts around 2 angstroms. You need it at 1/2 micron for the light to notice.
So I need to multiply the length by a couple of thousand, raise a couple of thousand to the power of 1/63 hundredths, and you get a couple of 100,000. So the fraction has to be a few parts in 1,000,000. At 318 Kelvin, that is about 1,000th of a degree.
About 1,000th of a degree, which is why the demonstration works. The whiteness comes on well before that, since the scattering builds as the patches grow. But for the patches to be genuinely the size of the light passing through them, you are a millikelvin out. That cell is showing you a few parts in 1,000,000 of its own temperature, with nothing but a hot plate under it.
The divergence answers the first of my 2 questions then, doesn't it? The froth appears because the correlation length runs away.
The froth is the correlation length running away, seen from directly above. Which is why I want to be careful about the word explains. I have named the divergence and given it an exponent. I have not said where the exponent comes from, and I certainly have not said why it should be the same number for a magnet and a fluid. Everything from here is that.
What is the obstacle precisely? Because I can write down the model, spins on a lattice, 2 states each, neighbours want to agree. That is the whole thing, and it has 1 number in it.
1 number, and in 3 dimensions, nobody has ever solved it. Be exact about why, because it is hard, is not a reason. Ordinarily, a problem has 1 dominant length, and you build your description around it. At the transition, there is none. The sample is doing something interesting at the lattice scale, at 10 spacings, at 1,000, at 1,000,000, all at once and all coupled. Every method anybody had assumed, you could pick a scale and work there.
So the difficulty is not the number of degrees of freedom. It is that all the scales are talking at once, and no one of them dominates.
That is the difficulty stated properly, and it is why the answer, when it came, was not a cleverer calculation, but a change in what you calculate. Leo Kadanoff had the idea in 1966, at Illinois, in a short-lived journal called Physics, scaling laws for Ising models near the critical temperature. The move is this: stop trying to solve the system, do something to it, and ask what it turns into.
Do what to it?
Look at it from further away. Formally, rule your lattice of spins into blocks, say 3 by 3 in the plane, 9 spins to a block, an odd number so there can never be a tie. Replace each block with a single spin and give that spin the value the majority of the block had. 6 up and 3 down becomes 1 up. Do it for every block. You now have a new lattice of spins, with a third as many along each edge.
I have thrown information away. 6-3 and 9-0 both become 1-up, and I cannot tell them apart afterwards.
You have thrown information away deliberately and irreversibly, and hold that thought, because in 5 minutes it stops being a defect and becomes the entire content of the subject. Now the second step, which people skip and should not. Your new lattice has a spacing 3 times the old. Shrink everything by a factor of 3 so the new picture has the old lattice spacing and you can lay the two side by side.
Because otherwise I am comparing a picture with a photograph of a picture, and any difference could just be the magnification.
Precisely that. Coarse grain, then rescale, so like is compared with like. Now the question that is the whole idea. You started with a rule. Neighbouring spins want to agree, with a certain strength, at a certain temperature. Your new block spins are also spins on a lattice, and they also have some rule governing them. What is it?
Something similar in spirit. The blocks that were mostly up sat next to blocks that were mostly up, since the original spins were correlated, so the block spins should also want to agree with their neighbours. The strength will be different.
Different, and that is the payload. One number went in, how strongly neighbours want to agree, measured against the temperature. One number comes out, and it is not the same number. The operation is a map. Hand it a system, and it hands you back a system of the same kind, with the knob turned. Kadanoff called the blocks block spins, and the operation, once Wilson had it, became the renormalization group.
Say why that is progress. Because it looks as though I have swapped one unsolved model for another unsolved model.
You have, and the progress is that you can now iterate. You are not asking, what is the answer? You are asking, which way does the knob move, and where does it end up if I keep going? A completely different kind of question, and answerable. And you can already do the two easy cases. Take a system at very high temperature, where every spin is independent and random. Coarse grain it. What do the block spins look like?
Also independent and random. 9 random spins have a majority that is essentially a coin toss, and neighbouring blocks share no information, so the new system is the same as the old. Random, uncorrelated. Very high temperature maps to very high temperature.
Now do it at very low temperature, where the sample is almost perfectly ordered with a few isolated flipped spins in it.
The majority rule kills the isolated flips. A block with one wrong spin in 9 comes out unanimous, so the new system is cleaner than the old one. The disorder is being wiped out, and iterating drives me towards perfect order. Very low temperature flows to lower still.
So the flow has 2 destinations already. Warm systems get warmer under the squint, and cold ones get colder, and each destination is a place the operation cannot move you away from once you are there. Those are fixed points, and they are the boring ones. But look what you have proved without doing any work. The flow runs away from the transition in both directions.
Which forces a watershed. If everything warm gets warmer under the squint, and everything cold gets colder, there has to be a temperature in between that goes to neither. And my transition has to be sitting on it.
It is sitting on it, and I want to establish that from the correlation length rather than assert it, because the argument is 3 sentences, and it is the most important argument in this hour. What happens to the correlation length under one squint?
I measure it in lattice spacings, and the lattice spacing has just tripled, so a patch that was 30 spins across is now 10 blocks across. The correlation length divides by 3.
Every step divided by 3. Now put that against the definition of a fixed point. A fixed point is a system the squint does not change. So its correlation length, whatever it is, must equal itself divided by 3.
Which only 2 numbers do, 0 and infinity.
Only those two, and nothing else is on offer. So every fixed point of this operation has either no correlations at all or infinite ones, and there is no third kind. Your two boring destinations are the zero case, and check that against the subtraction I made you do when we defined the correlation function.
At infinite temperature, the correlation is genuinely zero beyond one spin. At zero temperature, everything is aligned. So the raw product of two spins is 1, no matter how far apart. But I subtracted the averages, and the average is also 1, so the difference is 0. Nothing departs from the mean because there is no departing going on. Both boring fixed points have 0 correlation length.
Both of them, which leaves exactly one possibility for the watershed, and it is forced, a fixed point with infinite correlation length. That is the critical point, and now the logic runs the other way, which is much the better direction. The critical point is not the place where the correlation length happens to diverge. It is the place the flow leaves alone, and the correlation length has no choice but to be infinite there, because a finite one would have been divided by 3, and the point would have moved.
Say what that means about the sample itself, physically, because I have been doing bookkeeping.
It means the critical system looks the same at every magnification. Photograph your magnet at the critical temperature, froth and all, and hand it over with the scale bar removed. Nobody can tell you whether they are looking at 100 atoms or 100 million. Blotches inside blotches inside blotches, the same statistics at each level. Take the same photograph 1 degree away, and they can tell you immediately because there is a blotch size in it, and a blotch size is a ruler.
And the tube. That is the same statement, isn't it? The fluid is milky because there is structure at every size, and there is structure at every size because no size is preferred.
The tube is that statement in visible light. Scale invariance is not an extra property critical systems happen to have. It is what fixed point means, translated into a picture. And it goes the other way. If you ever find a system with no characteristic length, it is sitting at a fixed point, because a fixed point is the only place a scale-free system can be.
One thing about the word group bothers me. You said the operation destroys information. Then I cannot run it backwards, and a group has inverses.
It does not have inverses, and it is not a group. It is a semigroup. Compose 2 squints, and you get a squint, and that is all. The name is an accident inherited from particle physics, where the transformations were invertible. Wilson used it, it stuck. Consider it apologized for.
There is a crack in the block spin argument, and I want it opened. You asked what rule the block spins obey, and I said neighbours want to agree, with a different strength. I have no right to that. Why should the new rule have the same form as the old one?
It should not, and it does not, and that is the thing Kadanoff assumed away, and Kenneth Wilson would not. Coarse grain honestly, and the block spins acquire couplings you never put in. Next nearest neighbours, because 2 blocks that do not touch still share information through the spins between them. 4 spin terms. Weak couplings to blocks 3 and 4 away. Every interaction symmetry permits gets generated. Wilson's 2 papers in the Physical Review in 1971 are where that is faced. The first has Kadanoff's name in its title, and they are what the Nobel Prize of '82 was for.
So one squint takes a model with 1 number in it and turns it into a model with infinitely many. That is worse, not better.
It looks catastrophic, and it is the saving move. Stop thinking of your system as a model with a knob. Think of it as a point. Imagine a space in which every possible Hamiltonian is a point. 1 axis for the nearest neighbour strength, 1 for the next nearest, 1 per 4 spin term, 1 for every interaction symmetry permits. Infinitely many axes. A material at a temperature is 1 point in it. The squint moves the point, and squinting again moves it again, so each starting system traces a trajectory.
A fixed point is then a point in that space that does not move. Give me the picture of the flow, because trajectory in an infinite dimensional space is not something I can see.
Water on a landscape. Every point of the space carries an arrow saying where one squint takes you, and following the arrows is what a system does as you back away from it. The two boring fixed points are the bottoms of two valleys, the ordered basin and the disordered one, and almost everything drains into one or the other. Between them is a ridge, and on the ridge a pass, and the pass is the critical fixed point. Water arriving exactly there stays. Water arriving near it slides off, one way or the other.
Then the interesting question is, what happens near the pass rather than at it? Because no real material is exactly at a critical point.
Near the pass, and here is the machinery. Sit at the fixed point and nudge in some direction. Add a bit of next nearest neighbour coupling, say. Now squint. The nudge either got bigger or smaller, and there are only three answers. If repeated squinting grows it, the direction is relevant. If repeated squinting shrinks it away to nothing, it is irrelevant. If it does neither, it is marginal, and marginal cases are where the logarithms live.
Give me irrelevant as a physical statement rather than as a growth rate. What am I being told about the material?
That you can change that feature as much as you like, and nothing about the long-distance behavior changes. Picture two samples identical except for that one feature, photographed side by side. Squint once and they still differ. Squint 20 times and the two photographs are not similar, they are indistinguishable, and the blotches in both are doing the same thing. Not changes a little. The correlation length still diverges with the same exponent. The heat capacity keeps the same singularity, and only the coefficients out front shift. The feature has not been neglected. It has been deleted by the act of looking from far enough away.
Relevant is a knob I have to hold then.
A knob you have to hold, or you fall off the ridge. Now the count that organizes everything. For a magnet with two state spins in 3 dimensions, how many relevant directions has the critical fixed point? 2. One is the temperature, the other the magnetic field. Every other coupling anybody could write down is irrelevant.
2, and I can test that against something I already know. To find a critical point in a fluid, I have to tune the temperature and the pressure. 2 knobs, and if I get either wrong, I miss it, which is why it is a critical point on the phase diagram rather than a critical line.
2 knobs and a point, exactly. In a magnet, you also tune too. You set the temperature and you set the field to 0. Nobody thinks of that as tuning because a symmetric sample with no magnet nearby has already done it for you. The up-down symmetry holds the second knob at 0 for free. Same count, one of them hidden by a symmetry.
Where is universality in this? Because that is what I was promised, and I still cannot see it.
It is already done. You have everything. Consider the starting points that flow into the critical fixed point rather than sliding off. The ridge itself, which people call the critical surface. 2 relevant directions means it misses being everything by exactly 2 dimensions, so it is enormous. Take 2 of its points, as far apart as you like. One is a lattice of magnetic atoms, the other is a box of argon. Follow the arrows from each.
They both arrive at the same fixed point, which means every long-distance property belongs to that fixed point, and not to where either of them started. So the 2 systems have to agree. Do you mean agree exactly, or agree to within whatever the measurement can see?
Exactly, in the limit of getting close enough, and that is the only qualification there is. The exponents are properties of the destination. The starting point supplies the coefficients out front, the correlation length in angstroms, the transition temperature, the strength of the scattering. Those differ wildly between materials. The exponents are not material properties at all.
Then what can possibly distinguish one fixed point from another? Because if almost everything is irrelevant, the destinations must be scarce.
Scarce, and the list is short. The dimensionality of space, which the squint cannot change, since coarse-graining a three-dimensional thing gives you a three-dimensional thing. The symmetry of the order parameter, how many components and what leaves the energy alone. Because the squint respects symmetry at every step and can neither manufacture nor destroy one. And a third that is usually mumbled, whether the interactions are short-ranged. Make the force fall off slowly enough and you land elsewhere. Dimension, symmetry, reach. Everything else is flowed away.
Which is what the first hour of this series was promising when it said, effective theories are entitled to work.
It is the mechanism under that promise, and stronger than the version people usually carry. The usual story is that microscopic details are too small to matter, which is a plea for approximation. This is not that. They are removed by the act of changing scale, and what is left is the whole of the long-distance physics with nothing thrown away. That is why an effective theory can be exact about the things it is about.
What is the class called, so I have a label to use?
A universality class is the set of all systems that flow to one fixed point. The one we have been discussing is the three-dimensional Ising class. One component order parameter, a symmetry that exchanges its two values, 3 dimensions. In it, uniaxial magnets, the liquid-gas critical point of every simple fluid, binary alloys ordering, a mixture of two liquids unmixing. Nothing in that list resembles anything else in it, and it settles what I left hanging back at Landau's construction. Guggenheim's 8 liquefied gases, falling on one curve once each, was plotted against its own critical point. Plotting a fluid against its own critical point divides out the coefficients it supplies. What is left is the fixed point, and there is one of those, so there is one curve.
Stop on the fluid because I think you have just smuggled something. A magnet has a real symmetry between up and down. The Hamiltonian cannot tell them apart. A liquid and its vapor are not mirror images of each other in any sense at all. The coexistence curve is visibly lopsided. So where is the fluid symmetry?
It does not have one, and you are right to stop me. The fluid's up-down symmetry is not in the fluid. It is in what is left of the fluid after enough squints. The asymmetry between liquid and vapor is a set of terms in that infinite dimensional space, and every one is irrelevant. The flow eats them, and what arrives at the fixed point is symmetric, even though what set out was not. The symmetry that fixes the class belongs to the destination, not to the material. Stranger than the claim I made a minute ago, and the correct one.
An emergent symmetry, then. The system acquires a symmetry it never had by being looked at from far enough away.
Acquires it, and it is measured. The exponents of xenon and carbon dioxide are the Ising exponents, and those fluids are not symmetric under anything. Now use the tool yourself, because sorting perturbations into relevant and irrelevant is the one skill this hour is trying to give you.
Set me a list.
A three-dimensional magnet with two state spins sitting exactly at its critical point. I am going to modify it 4 ways. For each, say whether it is relevant, moving the system to a different fixed point with different exponents, or irrelevant. First, change the crystal structure. Take it off a simple cubic lattice and put it on a face-centered cubic one, so every atom has 12 neighbors instead of 6.
Irrelevant. The lattice is a statement about what happens at one atomic spacing, and after 20 squints my block spins do not know what lattice they came from. It will change the transition temperature enormously, and the exponents not at all.
Correct, and the transition temperature moves by more than a factor of 2. Second, add a weak next nearest neighbor coupling and a weak 4-spin term, an energy depending on 4 spins around a face of the cube.
Both irrelevant, for the same reason and a better one. Those are exactly the terms that coarse graining generates all by itself. If the flow manufactures them out of nothing and still ends up at the same fixed point, then starting with a few of them already switched on cannot possibly matter. I have just begun the journey a little further along the same road.
That is the better reason, and it is the right one. Third, let the spins point anywhere on a sphere instead of only up or down.
Relevant, and not marginally. That changes the order parameter from 1 component to 3, which changes the symmetry. And symmetry is one of the 2 things you said the flow cannot touch. Different fixed point, different exponents, and I would expect the correlation length exponent to come out somewhat larger, because a system with more directions to fluctuate in fluctuates more.
It does, and it goes to about 71 hundredths against 63. Fourth, randomly replace 3% of the magnetic atoms with non-magnetic ones. Dilute it the way a real alloy is dilute, with the vacancies frozen in place rather than moving about.
Irrelevant, and I will say why so you can hold me to it. It does not change the dimension of space. It does not change the symmetry of the order parameter, since the remaining atoms are still up or down. It is a small perturbation, 3%, and it lives entirely at the atomic scale, which is the definition of a microscopic detail. A patch 1,000 spins across the edge contains 1 billion atoms, and the vacancy density in it is 3% to very good accuracy, whichever patch I pick. So by the time the squint has run 20 times, the randomness has averaged itself into a constant. It is the most microscopic thing on your list. I would bet on it.
You would lose the bet, and the way you lose it is the most instructive thing in this hour. Your averaging argument is real. The vacancy density inside a large patch is close to 3%, and the spread does shrink as the patch grows. But it is a race, and you only checked one runner. The spread in local transition temperature from patch to patch shrinks as the patches grow. The trouble is that the distance you are from the transition is shrinking too, and the whole question is which of the 2 goes to 0 faster.
And if the spread wins, if the patches are still disagreeing about where the transition is by more than my distance from it, then there is no single transition temperature for the sample at all.
There is not. Different regions go critical at different moments, and the pure fixed point cannot survive it. Brooks Harris wrote the condition down in 1974 in the Journal of Physics C, and it is one line. Randomness of this kind is irrelevant if the heat capacity exponent of the clean system is negative, relevant if it is positive. So, what is the heat capacity exponent of a 3-dimensional Ising magnet?
Positive. About 11 hundredths, small but positive, and the sign is all your criterion asks for. So dilution is relevant, and I got it exactly backwards.
Exactly backwards, and the consequences are measured rather than argued. The flow leaves the clean fixed point and arrives at a different one, the randomly diluted Ising fixed point, where the exponents are genuinely different. The correlation length exponent moves from about 63 hundredths to about 68, and the heat capacity exponent changes sign to about -5 hundredths. Diluted magnets have been measured, showing the shifted numbers.
The sign change at the end is not a coincidence, is it? The new exponent is negative, which by your own criterion is the condition for randomness to be irrelevant. So the flow ran away from the clean fixed point because randomness grew there and stopped at a fixed point where randomness does not grow. It went looking for somewhere its own instability is cured.
It found the place where the instability is cured, and that consistency is one reason people believe the picture. Now say what your mistake was in a form you can carry, because it is more useful than the ones you got right.
That I heard microscopic details are irrelevant and treated it as a license when it is a calculation. Irrelevant does not mean small. That vacancy term is tiny everywhere in my sample, and it wins anyway, because what decides is not how big the term is. It is whether repeated coarse graining feeds it or starves it, and those are unrelated questions. A term can be enormous and starve. A term can be invisible and be fed.
That is the sentence, and the practical consequence is worth stating flatly. You cannot sort perturbations by inspection. You compute how each scales, or you look it up. Details do not matter is a summary of a calculation somebody has already done, not a substitute for doing it.
You have given me a machine for producing exponents in principle and not a single exponent. Can it actually produce a number?
It can, and the first clean thing it produces is a dimension rather than a number. The one I have owed you since Landau. Mean field theory is exact above 4 spatial dimensions and wrong below, and I could not tell you why. I can now, and it takes one idea.
Then start from Landau's free energy, since that is the thing that was wrong.
Start exactly there. Landau's expansion had 2 terms that mattered, one going as the square of the order parameter, whose coefficient changes sign at the transition, and one going as the 4th power, which stops the runaway. Put that into the flow. The square term is the temperature, one of the 2 relevant directions which we knew. The interesting one is the 4th power. Ask the only question this hour asks. Under repeated squinting, does it grow or shrink?
The answer will depend on the dimension, or you would not have brought me here.
The answer depends on the dimension and on nothing else. And the real version is a scaling count I am not going to speak aloud. What I will give you is the picture underneath it, which is a genuine argument and not a decoration. The 4th power term is how one fluctuation notices another. Without it, fluctuations pass straight through each other, and the problem is a set of independent modes, which is precisely Landau's theory. So does the 4th power term matter, is the question, do fluctuations run into each other?
Whether things run into each other is a question about how much room there is.
It is exactly that, and there is a clean statement of it. A fluctuation wanders through the sample the way a random walk wanders, and a random walk is a 2-dimensional object, not because it lives in a plane, but because of how it fills space. Take many steps and you finish about the square root of that number from the start. Turn it round. Inside a box of a given width, the steps a walk packs in grow as the square of the width. That is how a surface fills space, not how a line does. Now set 2 loose together and ask whether they generically meet. 2 objects of dimension 2 meet if 2 plus 2 exceeds the dimension of the space they are in.
Which is a statement about 4. Below 4 dimensions, 2 random walks cross each other constantly, so fluctuations interact and the 4th power term matters. Above 4, they miss, so fluctuations essentially never meet. The 4th power term dies away under coarse graining, and Landau is right.
Landau is right, and take the word right literally. Above 4 dimensions, the flow carries you to what is called the Gaussian fixed point. No interaction between fluctuations at all, and its exponents are precisely Landau's. The correlation length as the inverse square root of the distance to the transition, the order parameter as a square root, all of it. Mean field theory is not an approximation up there. It is the exact answer, because the thing it neglects is deleted by the flow.
Below 4, the Gaussian fixed point is still there, but nothing stays at it.
Still there and unstable. The 4th power term is now relevant, so the smallest amount of it grows under squinting and the system is carried away to a different fixed point with the interaction switched on. And that one has the exponents you measure. The same count says why Landau stopped where he did. Below 4 dimensions, the 6th power and everything above it is irrelevant, so the flow eats them, and the 4th power is the last term that matters. He truncated by instinct, and the flow says the instinct was right. So the failure below 4 dimensions is not a failure of arithmetic. It is a fixed point losing its stability, and the exponents change because the destination changed.
What happens exactly at 4?
Marginal. It neither grows nor shrinks at leading order, so it dies slowly instead of exponentially, and everything picks up logarithms. Mean field exponents with logarithmic corrections. A real case, and where a great deal of particle physics lives, but not ours.
And the criterion you gave me then, comparing the fluctuations inside a correlated region to the order parameter itself, is the same statement in different accounting.
The same statement arrived at by Ginzburg in 1960 without the flow. He asked when the fluctuations are small enough to ignore and got 4 out of it. Wilson asks whether the term coupling them grows and gets 4 out of it. One tells you where to trust the answer, the other tells you what to do when you cannot.
I still have no number. Everything so far tells me a fixed point exists and what it is not. How does anybody compute where it is?
With one of the great pieces of opportunism in theoretical physics, and it belongs to Wilson and Michael Fisher, both at Cornell. At exactly 4 dimensions, the 4th power term is marginal, so the interacting fixed point and the Gaussian one sit on top of each other. Drop just below 4 and they separate, but only just. The new fixed point is close to the old, and the interaction strength at it is small.
Small in proportion to how far below 4 dimensions I have gone.
In proportion to exactly that. So if you will treat the dimension of space as a knob you can turn continuously, rather than an integer handed to you, you have manufactured a small parameter, and a small parameter is something you can expand in. That is, the epsilon expansion, epsilon being the distance below 4. Wilson and Fisher, Physical Review Letters, the 24th of January 1972, under the title Critical Exponents in 3.99 Dimensions, which tells you they knew how peculiar it was.
That is the 3rd time this series has run into there is no small parameter, and the first time anybody has responded by inventing one out of the dimension of space. Does it work?
I am not deriving it, and I want to say what the derivation would have given you. At first order, it hands you the correlation length exponent as 1/2, Landau's value, plus 1/12 of the distance below 4 dimensions. Now be brutal with it. We live 3 dimensions below 4, so the distance is 1, which is not small by anybody's standard, and you have no right to stop at 1 term.
1/2 plus 1/12 is about 58 hundredths. The true value is 63. So a series I am not entitled to use, cut off after 1 term, evaluated at a parameter of 1, gets me roughly 2/3 of the way from mean field to the answer.
2/3 of the way, and that is the state of it. The series is asymptotic. It does not converge, and people have computed enough terms to watch it diverge. In practice, you take several orders and resume, which works well and has no guarantee attached. The precise modern numbers come from elsewhere, large-scale Monte Carlo, and since about 2012, the conformal bootstrap, which exploits a fixed point being invariant under a still larger set of transformations than mere rescaling.
Give me the best number for the correlation length exponent, so I know what the target is.
For the 3-dimensional Ising class, 0.629971, with the uncertainty in the 7th digit. A number for a magnet and a fluid and an alloy at once, computed from a fixed point rather than a material, and nobody has put it into an experiment that disagreed.
Then let me ask about the other exponents, because I have been given a list of them across this series, and they have never been connected to anything. Are they independent numbers?
They are not, and that was known before anybody could explain it. Benjamin Widham at Cornell, in the Journal of Chemical Physics in 1965, looked at fluid data near critical points and proposed that the equation of state is homogeneous. Scale the temperature and the density together in the right proportion, and the whole thing collapses onto one curve. He did not derive it. He proposed it because the data looked like that.
The consequence being relations between the exponents, so that if I measure two of them, I have already fixed the rest, and the collapse onto one curve is what a family of related exponents looks like when it is plotted.
Exactly that. And there is a handful of them, all checkable with a ruler. The oldest is Rushbrook's, and in words it says the heat capacity, the order parameter, and the susceptibility are not free to behave independently. Pin down how two of them diverge, and the third is already decided. It was proved first as an inequality from thermodynamics alone. Widham's scaling turns it into an equality. Fisher supplied another, tying the susceptibility to the correlation length. All of them were tested against data in the middle 1960s, and all of them held.
Where does the flow explain that? Because if the exponents are related, something must be limiting how many independent numbers there are.
Something is, and you already counted it. Two relevant directions. Near the fixed point, each grows at its own definite rate under one squint, and there are two of them, so there are two numbers and no more. Every exponent anybody measures is built out of those two. That is why the relations hold, and why the exponents were never going to be an unrelated list.
Which turns the chronology into something quite clean. Widham saw the pattern in the data and guessed the form. Kadanoff explained where the guess came from with the blocks. Wilson turned the explanation into something you could compute with.
And the three of them shared the Wolf Prize in 1980 for it. Wilson had the Nobel Prize on his own 2 years later for his theory for critical phenomena in connection with phase transitions, and there was some feeling at the time that it should have been shared the way the Wolf was.
The accounting I walked in with is now upside down, and I want it straightened. You told me Landau's construction has an expiry date, and the date is the transition. Today you have told me the transition is the only interesting thing in the problem. So what exactly is left of Landau?
Nearly all of it, and the split is sharp. Landau's construction has two parts that people run together. Part 1. Write the free energy as a function of a slowly varying order parameter, keeping the terms symmetry permits, with a quadratic coefficient that changes sign. Part 2. Minimize that function and call the answer physics. Part 1 was never what was wrong. It is right, for the reason we found today. The terms symmetry permits are exactly the terms that survive coarse graining, so Landau wrote down the correct long wavelength description 35 years before anybody could say why he was entitled to it. Part 2 is the error. Minimizing means choosing the single best configuration and ignoring every other, and near the transition, the others are the froth. The renormalization group replaces that step. Instead of minimizing, you sum over the fluctuations, shell by shell, shortest wavelengths first.
That contradicts what you told me at the time. You said that below 4 dimensions, the constrained free energy is itself not analytic, so the series was never entitled to exist. Now you are telling me the series was right all along. Which is it?
Both, because they are two different objects, and I should have separated them then. What Landau writes down is the free energy coarse-grained to some short distance and stopped there. Nothing summed over yet, and that one is analytic. The one that is not analytic is the exact free energy with every scale in it. Producing the second from the first is precisely what the flow does. The non-analyticity is not a flaw in what he wrote. It is the output of the step he did not take.
So Wilson did not write a rival theory of magnets. He told you what to do with Landau's.
That is the cleanest way to say it, and it goes further than a rescue. Above 4 dimensions, the flow says, minimizing was right all along, so it does not merely repair Landau, it certifies him and hands you the boundary of the domain, which is the one thing an effective theory can never supply about itself. Everything structural from that hour is untouched. The order parameter, the rule that a cubic invariant forces a first-order transition, the trough in the wine bottle, the Goldstone modes, the rigidity. All of that is about what a transition is allowed to be, and the flow does not change what is allowed. It changes the numbers near the transition, and nothing else.
And it explains the thing that used to look like luck. That mean field theory is essentially exact for an ordinary superconductor, which we leaned on heavily last time.
Essentially exact, for a reason you can state in one sentence. The correlation length in a conventional superconductor is thousands of angstroms, so the region where the froth matters is a part in a million of the transition temperature, and nobody will ever be inside it. Ginzburg-Landau is not a lucky approximation. It is mean field theory used where the flow says mean field theory is correct.
Give me the honest state of the subject then, because everything you have said today has been a success story, and I do not believe there are no loose ends.
There is one that has not moved in 20 years, and it is embarrassing precisely because it involves the best measurement. The superfluid transition of helium belongs to the two-component class rather than the Ising class, and its heat capacity exponent is the most precisely measured critical exponent in physics. The flown experiment we discussed, analyzed by Lieper and colleagues, giving about -13 thousandths. Theory has since nailed that class to 5 digits. Monte Carlo and the conformal bootstrap agree with each other and give about -15 thousandths.
Which is a disagreement, not an agreement.
About 8 times the stated uncertainty, and it has stood for 2 decades. Either there is a systematic effect in a measurement made in orbit that nobody has found, or something in the theory of the two-component class is missing. Nobody knows which, and there is no route to another shuttle flight.
Let me take the Milky tube apart and see whether the hour is inside it. Warm the cell towards 45 degrees, and the correlation length, the size of the biggest patch that has momentarily agreed to be denser than average, starts at a couple of angstroms and grows as a power of how far I am from the critical temperature, with an exponent of about 63 hundredths. By 1,000th of a degree out, it is half a micron, which is the size of the light I am shining at it. And it has not gone from small to large. It passed through every size between and left them all switched on, which is why the scattering is total. The whiteness is a length running away in front of my eyes.
And the exponent in that sentence, where does it come from?
From a fixed point of an operation, not from sulphur hexafluoride. Rule the system into blocks, replace each block by its majority, shrink the picture back to the original scale, and ask what rule the new spins obey. Repeat. The correlation length divides by 3 each time, so anything the operation leaves alone must have a correlation length of 0 or of infinity, and the critical point is the one place with infinity, which is why a critical system looks the same at every magnification. The exponents are properties of that fixed point. The fluid only supplies which fixed point it drains into.
And the coincidence you refuse to accept at the start
Is not a coincidence and is not even a resemblance. The magnet and the fluid are different points in the space of all possible Hamiltonians, and almost every direction in that space is irrelevant. Coarse graining shrinks it to nothing. So both are carried to the same destination, and everything measured near the transition is a property of the destination. Only 2 things about the journey survive: the dimension of space and the symmetry of the order parameter. And in the fluid, the symmetry is not even there to begin with. It is manufactured on the way, because the terms that spoil it are among the ones that get eaten.
which is the item I would most want you to hold, because it is the one people get wrong. Universality is not a statement that microscopic details are too small to notice. It is a statement that they are removed.
The correction I earned the hard way goes next to it. Irrelevant is not a synonym for small, 3% of the atoms missing at random is as microscopic and as feeble a perturbation as anything on your list. And it changes the exponents because the flow feeds it, and what the flow feeds has nothing to do with what is large. I cannot sort perturbations by looking at them.
You cannot, and neither can I. Now the thing you could not have asked me 2 hours ago,
Whether Landau was wrong. I would have said yes an hour ago because the exponents are wrong and the exponents are the measurable thing. I now think the question is badly posed. Landau wrote down the right object and then did the wrong thing to it, and the wrong thing was minimizing instead of summing over the froth. Above 4 dimensions, minimizing is correct because 2 random walks in that much room never meet, so the fluctuations never notice each other. Below 4 they meet constantly. 4 is not a number somebody fitted, it is where an exponent changes sign.
all of that, and one limit that belongs beside it, because it is the price of the method. Nothing today predicts a critical temperature. The flow tells you which destination a system reaches and nothing about how far it had to travel. So every number a chemist would actually want is still measured rather than derived. Which leaves one place to go. Everything in the last 4 conversations has been built on one object, a quantity that is 0 on one side of a transition and not 0 on the other, a choice the system made. Broken symmetry, order parameter, free energy expansion, today's flow, all of it needs something to have been chosen.
And you have been promising since the first hour that there are states of matter where nothing is chosen at all.
Where nothing is chosen, nothing is broken, and no quantity grows out of 0. And 2 such states are still, demonstrably, not the same state. Nothing for the flow to grip and no order parameter to coarse grain, and the distinction is real and measurable to a precision that makes today look sloppy. What separates them is not what the wave function is at any point. It is what it does to itself when you take it slowly round a loop and bring it home. Take a single spin, walk it round a closed path in a magnetic field, and set it back exactly where it started. Next time we find out what it brought with it.